let's see the pH and the buffer solution. The proton, yeah, this is the formula you need to remember about. And nanometer to 10 to the minus 9, and micromolar 10 to the negative 6, and millimolar 10 to the negative 3. And weak acid is acid. We know the acid is the high proton donor, and the base is the proton receptor. So weak acid, you can see that like HA, and conjugate base is like A minus. And the important focus is the protonation. We know that when the pH is low, there are lots of proton in the solution. So we want to protonate different functional group. And deprotonation is the opposite. When the pH is high, there isn't so many proton in that, so we want to deprotonate. When the pH is low, some of the functional group, they are not neutral, as the amine. Because amine have a really high pKa, and they can add on a proton on their functional group. So if you take a look at some nitrogen, you need to think about, it is neutral, can it gain some proton or not? Yeah, and the Ka is the amount of dissociation, and pKa is the negative log. If you dissociation a lot, that means you are strong acid and your pKa will be really low. And there's another focus is the pKa. pKa tell you the pH at which functional group will lose or gain its proton. So low pKa are protonated at physiological pH. Because pH equal to 7.4 is not that low, so there is so many proton in that, so we want to deprotonate it. And there's a very important equation of that. There's the Henderson-Hartzenberg equation, and it can tell you the mixture of the weak acid and its conjugate base. And this is the buffer. And the buffer can resist the change in the pH and maintain the protein structure when you put the protein in like the buffer. The buffer solution can react with the acid and don't change the structure of the protein. And there was a very important equation, not quite equation, it's like you need to understand is when your pKa less than the pH, means pH is high, so there are less proton in the solution, so you have more deprotonated molecule. So your conjugate base, that means the A minus will be more than your acid. And for buffer, if you are +1 or -1 pH around your pKa, that was a good buffer. If your pH equal to your pKa, that means there are 50-50 mixture of your weak acid and conjugate base. And at the physiological pH, the carboxylic acid, they are deprotonated because we know the pKa of the carboxylic acid is really low, so the 7.4 is above the carboxylic acid, so they want to deprotonate, they want to lose their proton. But for the ammonium, we know the amino group, their pK is really high, so the pH will lower than their pKa, so they want to gain proton. So this is a protonation reaction. And the Zweiter ion is the neutral molecule that have separate positive and negative charge on their functional group, but their net charge is 0. And we need to know at the physiological pH there for amino acid, their charge. They are not Zweiter ion. It's the lysine, the arginine, the aspartate, and glutamate, because they have the charge on their side chain. And histine, it is a more tricky amino acid because it can change their property due to when it is put in different solution. So how to calculate the isoelectric point means when the solution is 100% Zweiter ion, what is your pH? And you need to take the two close pKa and divide it by 2. And we know our blood is also a buffer. Our blood contains lots of bicarbonate, and we know the bicarbonate it can gain proton and it can lose proton, so it is a really good buffer. So when the pKa is 6.4, that means you lower than the pH. That means you have lots of proton, so you wanna protonate the bicarbonate, so the major molecule in your solution is the carboxylic acid. And when the pKa is 10.2, that means your pKa is higher than your pH, so you don't have so many like protons, so you wanna deprotonate. So the majority in your solution is CO3 2 minus, and there's a 4 effect. Means when the pH is low, oh yeah, this is the example like for the hemoglobin. Then when the pH is low, the histine 146 will form the salt bridges as the aspartate 94, and they will release the oxygen. So that's why